What is dark matter? The nature of dark matter is a great scientific mystery. We know it's something massive, but it doesn't leave an electromagnetic signature, consequently, it is not directly observable. However, these seemingly mysterious characteristics offer intriguing conceptual possibilities. In this episode, we shall explore a new possibility regarding the nature of dark matter. Let's begin our journey. In order to save time and prevent duplication, we shall leverage off as much existing information as possible. Hence, prior to proceeding, we recommend that viewers review episodes 17 to 20. With these episodes freshly in mind, and all recommended artifacts referenced in these episodes also reviewed, we're in a position to move forward. The standard model of cosmology conceptualization of the universe appears on screen. It's intuitive, simple and very easy to comprehend, however, it is profoundly limiting. A significant problem with this representation is that it does not visually communicate any aspect, or even the existence, of the quantum vacuum, let alone the quantum vacuum ground state, that is, the zero-point field. The standard model of cosmology representation of the universe is derived from general relativity. Unfortunately, the future of cosmology is not general relativity. The future of cosmology is the quantum vacuum, that is, the integration of general relativity with quantum mechanics. The most obvious integration point between these two disciplines is the quantum vacuum. It is important to note that, in the standard model of cosmology conceptualization shown, the diameter of the sphere denotes the size of the observable universe, that is, approximately 92 to 93 billion light-years. Illustrated on the right-hand side of the screen, is the quantum model of cosmology. The quantum model of cosmology is an equivalent representation of the standard model of cosmology, but also includes the quantum vacuum. The quantum model of cosmology is a sphere of Hubble radius, enveloping the quantum vacuum. Specifically, the quantum vacuum in its ground state, termed the zero-point field. The radius of the sphere changes with Hubble time, and the observable universe rests upon the surface of the sphere. This means that, in order to circumnavigate the observable universe, a traveler must move all the way around the sphere, returning to their starting position. By doing so, the traveler has moved approximately 92 to 93 billion light-years, which is equal to the diameter of the standard model of cosmology conceptualization on the left-hand side of the screen. In other words, the perimeter of the quantum model of cosmology equals the diameter of the standard model of cosmology. We exploit this relationship in order to derive some astonishing experimentally verified results, thus proving that the true age of the universe is the Hubble age. Now, I'd like to draw your attention to the cosmic web. As you can see, inside the standard model of cosmology sphere, a spider's web appears to have been woven. These apparent threads of silk are in fact large-scale galactic structures strewn throughout the universe. The obvious question is, why do these structures appear to be distributed along certain lines? Why are they not distributed homogeneously throughout the universe? We'll answer these questions momentarily, but ask yourself, beyond looking like a spider's web, what does this situation resemble? To make the question a little more specific, what does this pattern resemble two-dimensionally? Let's investigate one possibility on the next slide. A moment ago, we questioned the two-dimensional resemblance of the cosmic web. Well, if we take a sheet of blank white paper, and scrunch it up into a ball, we can simulate the universe at an instant prior to the Big Bang. We'll call this scrunched-up paper ball the Big Bang singularity. Next, we will simulate cosmological inflation and expansion by opening up the scrunched paper ball into a quasi-flat, that is, almost flat, sheet of paper. Once we do this, we can see that the wrinkles in the sheet of paper yields a two-dimensional resemblance to the cosmic web on the previous slide. With this analogy in place, let's turn our attention to general relativity. According to general relativity, what does the presence of mass do? Well, it curves space-time and leaves no electromagnetic signature. Therefore, the observed effects of dark matter are indistinguishable from space-time curvature. We term this the curvature equivalence principle. Our principle is fundamentally no different to the equivalence principle proposed by Albert Einstein. Hence, if you disagree with our proposition, You must also be prepared to abandon Einstein's version, in order to remain logically consistent. Let's consider that at the instant of the Big Bang, dark matter was created in the form of filaments and clumps. By applying the curvature equivalence principle, these features may be described as wrinkles in the fabric of space-time. At the instant of the Big Bang, dark matter existed in high wrinkled density form. The wrinkles on the flattened sheet have been stretched by cosmological expansion to a state of lower wrinkled density. These wrinkles act as an energy source by decaying to dark energy, hence, feeding the zero-point field as cosmological expansion continues. Eventually, in the far distant future, the wrinkles will disappear as the dark matter decays to dark energy. So, just to be clear. Firstly, dark matter decays to dark energy. Secondly, dark energy is a pseudonym for the quantum potential energy stored in the zero-point field. Thirdly, this quantum potential energy manifests as virtual photons popping into existence. And lastly, virtual photons are experimentally observable via the Casimir effect. Utilizing the Milky Way as an example, the dark matter halo denotes a region of more wrinkles, relative to intergalactic space having less wrinkles. Therefore, in accordance with the curvature equivalence principle, the dark matter halo is identical to a region of greater residual space-time curvature, that is, residual means, left over from the Big Bang. We've spent a bit of time proposing a novel solution for the nature of dark matter. The next obvious question is, what is space-time curvature? Under the curvature equivalence principle, the observed effects of dark matter are indistinguishable from space-time curvature. Now we pose the question, what is space-time curvature? You'd think that this question is obvious and the answer was provided by general relativity, but that isn't actually the case. Here is general relativity expressed in compact tensor form. This equation is a shorthand mathematical description of the very famous Einstein solution. It takes years to master and is profoundly limited. It says nothing about the mechanism for matter to curve space-time and does not in any way explain why, precisely why, matter curves space-time. So, it appears that general relativity raises another question. What is space-time curvature? Well, if dark matter is identical to space-time curvature, then baryonic matter is identical to space-time curvature as well. Therefore, how do all forms of matter actually curve space-time? What is the common mechanism? We propose that all matter curves space-time by evaporating mass in the form of gravitons. Hence, space-time curvature is the resultant action of gravitons being absorbed by the zero-point field, also termed the quantum vacuum. Graviton absorption into the zero-point field obeys the inverse square law. We insist that gravitons are massive particles which interact with the zero-point field, that is, they interact with the space-time manifold, they do not interact with objects and they do not mediate the gravitational force between objects. The mass energy of each graviton is non-zero, and the minimum graviton evaporation period for all forms of matter is approximately 10 to the power of 13 gigayears. Please review episodes 6 and 19 for more information. So, what does all this mean with respect to the question of dark matter? Well, we propose that the regions of highest baryonic concentration, that is, highest gravitonic concentration, follow the filaments and clumps appearing on the Cosmic Web Standard Model of Cosmology diagram on slide 2. Moreover, we propose that dark matter may actually be wrinkles in space-time curvature, left over from the Big Bang, in the form of residual gravitons. Thus, in our proposition, gravitons were formed at the instant of the Big Bang, and are now decaying into dark energy. However, during their decay period, they appear indirectly as the space-time curvature we associate with dark matter. Therefore, as we state in our premise, the effects of dark matter and baryonic matter are identical to the effects of space-time curvature. And specifically, dark matter is indistinguishable from space-time curvature. Let's now summarize what we have learned. 3 forms of mass energy were created at the instant of the Big Bang. Their proportions are 50% dark energy, 44% dark matter and 6% baryonic matter. In this episode, we have identified that dark matter is indistinguishable from space-time curvature. We term this the curvature equivalence principle. Hence, potential explanations for dark matter created at the instant of the Big Bang could be wrinkles in spacetime, or filaments, clumps and halos of gravitons left over from the Big Bang. In addition, in previous episodes, we have identified that some continuous cosmological processes might be baryonic matter decays to dark matter decays to dark energy, and dark energy drives cosmological expansion. For viewers wishing to consult publications relevant to this episode, you may do so by accessing the links shown.